Okay, so we're picking up a couple of sections in. We should have tried the free response, just the first free response problem, in 15 minutes. I did say one problem is 15 minutes. I think that second problem is just too much. I wasn't going to punish you with it. Look at that second problem really fast. A string wrapped around a solid cylinder. If you in-person students would like to see me suffer through it, I would do it myself just to show you. Yeah, it means you have to take notes on it if you're curious how it's done. And then maybe I'll even record it for the virtual students. Yeah, the block is wrapped around a cylinder. We will, before we shuffle on from mechanics and Atwood's machines and rotation, we will confront this problem because I've seen it appear in some form or another. We have a cylinder and we drop a block. The block does not descend at G, but it's a cylinder that's free to rotate. So it's only the rotational inertia that resists the cylinder. So it's an Atwood's machine that has no block on one side and it has rotational inertia on the pulley, and that's all that slows you down. How much is it? Whoa. I don't expect you to remember that or have any idea how to do it. But this first one just has blocks on a ramp. Okay? Be honest. You're in AP Physics now. If you forgot mg sine theta, you probably should. You either need to resign yourself to studying a lot extra, or you need to say, okay, maybe I'm in over my head. Mg sine theta was a big deal. We went over and over it. Okay, pretty automatic. If you kind of forgot the friction coefficient, mg cosine theta is the normal force. Um, that's forgivable for now. Okay, and then so we have our normal force times friction. Good, good, good. Today, okay. Warn me before the end, because I can't see a clock in the back of my room. With at least 10 minutes to go, let me give you the answers to the free response. Okay, so we can see how they're scored. Okay, whoops, let's look real fast. Okay, so we had two blocks. It says they're in equilibrium. It gives the masses. Calculate the angle. It's just the inverse sine of the ratio of the masses. Pretty good, and we can get there pretty fast. Okay, now we've got mg sine theta and the coefficient times mg cosine theta. They both point down the ramp because friction opposes motion, and so the hanging block is trying to drag the other block up, but it remains in equilibrium. Well, that even trying to drag up, like this is, AP students miss all the time. I forgive you, it's fine. But really, we should be able to handle this. If something is rolling without slipping, the motion that's being resisted is the slipping. Like it should be slipping if there was no friction. So friction opposes, however, that surface would slip if there were no friction. But they stumped people over the summer. One of the questions was this thing rolls without slipping. What direction is, and it's like rolling up a ramp or upside down or something weird. What direction should the friction vector point? And everyone gets it backwards because they want to say, okay, friction is pushing this thing, it's rolling. Oh no, it doesn't have an engine, so it's not pushing off of friction. Friction is opposing the slipping. So we'll see if I can get this one right. Part C. Now block 1 will accelerate up the inclined plane. Let's sketch that real quick. So we have block 1. Now it's going up because there's a force of tension due to the other block. I'm still going to have mg sine theta pointing down. If it's accelerating up the ramp, then I also have to have friction going back. Okay, derive an expression for the magnitude of the acceleration. What? Okay. Force of tension. Oh no. The force of tension on this string is going to be the mass of block 1 times its acceleration plus, oh no, no, no. That's not right. The net force is the mass times acceleration. Mass times acceleration of block 1. M1A equals the force of tension minus M1G sine theta minus force of friction. Okay. So we've got tension applied, it does accelerate, it's got mg, it's got force of friction. On the hanging block, it's going to be the same force of tension. Right, so we could free diagram the same block, the second block, force of tension, and then we've got just m2g. And it's going to have the same acceleration. There's probably a shortcut here, but I'm dazed somehow this morning. Let's make sure I'm answering their question. Derive an expression for the magnitude of the acceleration of block 1. Oh, we're solving for A. Maybe I can just replace the force of tension, right? They're connected by the string, so they have to have the same acceleration. This is just one object, really. It's got a big string in the middle. Physics strings are not stretchable. They're not rubber bands. They really connect. Okay, so we would also say that m2g minus force of tension equals m2a, right? We're just acknowledging that they're connected by this force of tension, and I'm not calculating all external forces on one object, right? They're interconnected by this force of tension. I think that's reasonable. I could be wrong. Stay tuned. Okay, but force of tension equals m2 times g minus a. See that? Same m2s, tension's holding it up, gravity pulling down, and that results in the same acceleration. Okay, so I'm not exactly sure what the force of tension is going to be. I'm not sure I care what it is, because look, we can just substitute. Derive an expression for the magnitude of the acceleration of block 1. Yeah, so I have to use these and physical constants. Physical constants means g. It does not mean force of tension. So that's why I'm messing with all of these equations. I can't include that f of t in my answer. Okay? And then this is AP Physics. Oh, I'm going to have to collect terms. So this gets substituted in there. I'm going to have an m1 plus m2a. So if I solve it, let's go big brain. I'm going to have m2g plus m1g sine theta. Oh, I could simplify that, but I won't. We're running out of room, so I'm going to be bad and put m1g, well, mu times m1g, mu k, kinetic friction. Now the static one is gone. Mu k, m1g, cosine theta, all of that added together, bad math syntax, sorry, over m1 plus m2. Hey, it looks like I added up total forces and divided by the total mass. Seems reasonable. And I'm under time pressure, so I'm kind of going to go with that. Derive an expression for the tension in the string. Oh, I needed that. It's like I glanced ahead. I need this force of tension. Well, now that I know A, there's an easy way to substitute. Force of tension should be m2 times A. I would just rewrite this, multiply by m2, and then subtract m2g. Does that cancel any m2g's? I don't know. No, to make a common denominator. And it doesn't say, do we simplify? Let's look it up. Oh no, did I? Oh. have a bunch more, but it may be not enough. Okay. Part C. Oh, look, there's the sum of the forces. Oh, wait. Oh. Oh. Okay, that's a Newton's second law equation. Substituting the force of friction in F sub F, or they like lowercase f. Hooray, I got a point. 1 point for correct substitution of normal force. Yay, I did that too. Okay. Oh, man. So this part 1, all I had to do was normal force substitution correctly. Although, look, they do have my big equation. Although, oh no. Yeah. Those guys, I don't think I'd lose a point, but it'll be helpful for you to know. These two guys are still negative, these two terms. Why won't it keep my skinny pen? Those are negative. Otherwise correct. Wow. Okay. Derive an expression for the tension. Yep, and they're just going to use this. Force of tension equals m2g minus m2a. What a mess. They don't simplify it. Okay, so you're going to have this m2g blah, 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 blah. You don't have to make it a nice, pretty fraction. They have like m2g times parentheses 1 minus most of that. Yeah, times 1 minus that. Yuck. They didn't make common denominators. Okay. Okay. Looks like I'm getting all the points so far. Those negative signs wouldn't have cost me, because they know you're going crazy fast. It's just, are you using physics principles? Are you making correct substitutions? So they're a little more lenient. Okay, so what I feel like I have to teach for multiple choice is speed, because it's really hard to get those answers chosen and bubbled that fast. Okay, it's a big step up from honors physics. Sorry. But I feel like I push honors physics enough. With free response, I have to teach you perseverance. Just keep trying to answer the question. Even if you got that 19.5 angle wrong on the first one, you got 10 degrees or 30 or whatever, just keep using that. You'll only lose 1 point. And if you need that number for later parts, you'll get full credit. This is the answer I got for part A. Just keep using it. Okay, any questions? Right. It's almost like speaking a foreign language, and now we have to be fluent. On the axis below, sketch the speed and distance moved by block 1 up the incline as a function of time. Hey. Okay. It's going to accelerate up, right? I wouldn't waste time writing that out, but it's going to accelerate up the incline. Will it have constant acceleration? Will the friction change? No, the normal force won't change. Will mg sine theta change? Nope, not till it hits the pulley. What about gravity, m2? No, that won't change. Nothing will change. It will be constant. Just do a quick checklist in your brain. So, we should start at 0 and just go straight line up. Increasing speed. Up the plane. Yep, as a function of time. And if I'm increasing velocity, then I should just have parabolic, concave up, increasing distance. Distance moved. And it starts from rest. Pretty sure. Let's see if they made a fool of me. Nope, that's what they say. 1 point for a straight line graph with a positive slope. They could have asked a point for starting at the origin, but they didn't, and 1 point for a concave up graph on d versus t. They like to give gimme points a lot. So I think the gimme points were writing down Newton's second law equations for this one. But they could also pick, okay, it's a point just to start these at the origin. It starts from rest, etc., etc. Good. Almost at the end. Oh no. This is the same problem. So this is a medium problem. That's, but by the time we practice block on a ramp with friction, without, sliding up, sliding down, all this craziness, we'll go over it all again in AP, so you're solid. Those first four parts should actually be a breeze. Okay? It's kind of coming back to you now. Like, okay, if I saw that question, or even some small variation of it, that's pretty easy. I need a yes or no, thumbs down. Some people are just looking around. Okay, that's okay. Uh, that tells me I can't skimp on time when we're actually doing these problems. But we'll do enough of them that you'll be mad at me, which is good, and then you won't be able to forget the mu mg cosine and the mg sine theta. Okay, then they're going to throw a curveball at the end. And this is usually like, okay, now we want to see if the really fast super duper Whitcomb people, can we trick them at the end and see who really deserves like a 5 out of 5 or who gets a 4? Honestly, if you were rock solid on those first four parts, you don't even need this part. Maybe they're trying to get you to waste time instead of going on to the other questions. On the real test, it's 3 multiple choice questions all in 45 minutes, non-stop. Okay. Students collect data that shows the acceleration actually increases. While the blocks are in motion, it goes faster and faster. Oh, why might that be? Sketch the speed of the block as a function of time. So it would be increasing, but now it's going faster and faster as it goes. So now even the speed is concave up. Don't worry, and if you haven't heard, now wait a minute. Who has heard of concave up before? Heard those words before I introduced them today? Oh, everybody. Okay. So you did learn that in math class. We don't have to start there. Okay. Explain why the experiment may have produced an increasing acceleration instead of the predicted constant acceleration. Oh, and this picture, can I slice this out? This goes to the next problem. Okay. This brings me to the last part, explain. You sometimes are going to have to explain or justify with words. You can put in physics symbols or equations. They understand that you don't have much time to write. Some people insist on trying to write a book. All right. But you do have to actually put your thoughts on paper and someone will evaluate them. An increasing acceleration instead of constant acceleration. Guess what? Any realistic assessment will actually be right. I'm going to bet. So you don't really have to analyze the question that carefully. Okay? What I might say is the coefficient of kinetic friction decreases with temperature. Or speed, or well, I wouldn't do that as a final answer, but like a smooth patch on the incline. To move up faster, a simple reason might be the coefficient of kinetic friction is less. So there's less friction as you go up. That can happen as the block heats up. It's somehow slicker. There's like oil or grease on it or something yeah, even just a little bit. Or maybe the incline is getting smoother as you go up. There's less friction because of that, something like that. But it could even just be, oh, the students are timing it wrong, or the measuring system failed. Why in an experiment would produce an increasing acceleration? You could just say like your time instrument is failing and your seconds are too short, and so it looks like your speed is greater when really it's not. Let's see let's see what they say. You have the freedom to criticize like any reasonable situation you can come up with that might predict less acceleration or might record less acceleration. That should work. Question 1. Let's see what they have to say. Okay, 1 point for a concave up curved graph. Explain why it may have produced increasing acceleration instead of the predicted constant acceleration. Oh! 1 point for providing evidence to support the claim. And they exactly have the incline is smoother. They like my third choice there. Acceptable evidence. The block's acceleration. Oh, so. Ah. The incline is getting smoother. Okay. That's literally there. But I would have to accept any reason you can think of why kinetic friction decreases. Okay. Examples of acceptable evidence. They literally, the block's acceleration increases. They, you could just put, it really does increase and make up some physics reason why. The ramp is getting smoother as it goes up higher. It wasn't rough enough. Okay, the net force on the block increases. Okay, because there's less friction. But you could just state that. Greater friction indicates a rougher surface, or you could just describe friction. This is what it says. Greater friction indicates a rougher surface, less friction indicates a smoother surface. Wow. Okay, so your explanations, they don't have to be on point. They have to be anything reasonable and real in physics. And so it's my job to actually get you, it's going to be complicated this year. We need to do enough hands-on experiments that you realize all kinds of stuff can go wrong. And I can really just write anything realistic to make up an experiment, and you probably expect it to go wrong a few times, and that's fine. Like, College Board realizes that. That's really what they want. Okay. Oh, and 1 point for, so 1 point for the graph, 1 point for saying somehow the net force up the incline is increasing, whether there's less friction or whatever. And then correct reasoning. Okay, smaller resistive force, smoother surface. Okay, you can't claim that block 2 is getting heavier. I would have also just accepted like data taking error, mistiming. Like if the timing is, if your velocity timers, like if you meant to judge velocity and you space them too close together or too far, too close in time, that would work. Okay. Any questions? I will record that one. How close are we to 46? Oh no, it's almost time. I'm going to give you the answers. We'll start, in the book, we'll start chapter 3. So either have your paper book here tomorrow or bring technology that can do the PDF.